Welcome to Theory of Computation. This is lecture number 15. In the last lecture, we started with a curious puzzle. We asked ourselves if we could write a program that when we run will print a copy of itself. This puzzle was quite challenging and difficult to solve. We were able to solve it, and the rough idea was that if we look at the following instruction, print the following statement twice, second time in quotes, and in quotes it's written print the following statement twice, second time in quotes, and we follow this instruction, then this instruction reproduces itself. So we were able to make a program that when we ran it reproduced a copy of itself. After that we did something different. We proved what we call the recursion theorem. The recursion theorem roughly said that if we have a program that analyzes other programs and takes some data along, we can use that program to construct a different program which does the same analysis on itself. Roughly what the recursion theorem is saying is that a program can have a copy of itself. It can look at it, it can analyze it, and it can compute with it. That was the spirit of recursion theorem. On the face of it, recursion theorem does not seem like a very powerful tool, but we will use it to obtain many results in undecidability and decidability theory. Let's start. Today's lecture is going to be on the recursion theorem. We will first look at the statement of the recursion theorem and understand it fully. After that, we will apply the recursion theorem to obtain very interesting results. That would be the end of recursion theorem, and from then on we will start talking about logic and decidability issues in logic, which is going to be a very interesting subject. So let's begin. Let's look at the formal statement of the recursion theorem and understand it fully. Let T be a Turing machine that computes a function little t which maps sigma star cross sigma star to sigma star. Then the recursion theorem claims that there is another Turing machine R that computes a function little r which is going only from sigma star to sigma star, where for every w, r of w is going to be equal to t of the description of r comma w. So this Turing machine R does the same analysis that the Turing machine capital T was doing on its input. But R is not given itself as an input. So R is a self-analyzing program. Roughly, the recursion theorem is saying every program is allowed to get a copy of itself, or in other words, intuitively, we can add the following statement to our jargon, to our programming jargon, which is get a copy of itself, get your own description. Let's look at what the recursion theorem is saying intuitively. T analyzes a program. R does the same analysis on itself. Let's look at an example. Let us define a Turing machine in the following way. On input m, w, so this Turing machine gets a description of a Turing machine and some other input. Suppose this Turing machine counts the states in m and prints the number of states. So we have made a very simple Turing machine which gets a Turing machine as an input. It counts the number of states in that Turing machine and prints that number. Well, the recursion theorem says that now what you can do is you can make a new Turing machine which is called R, which when you run will actually print out the number of states in R. So it would do the same analysis that T was doing on other Turing machines. R would not need to be given its own description as an input. It would simply print out the number of states that it has. Let's look at another example. Let us consider another Turing machine T. Suppose that on input m, w, this Turing machine does nothing but print m. So T is a very simple Turing machine. It gets a description of a Turing machine and possibly some other input. It completely ignores the other input and takes the description of the Turing machine and simply prints it. So whatever description it gets as an input, it prints it on its output tape. The recursion theorem says now that there is another Turing machine R, which will on any input print its own description. The recursion theorem says that there is a Turing machine capital R which computes a function little r such that R of W is equal to T of description of R comma W. But T of description of R comma W is just the description of R. Therefore, this machine prints its own description. So, the recursion theorem is a powerful tool. Using it, we were easily able to convince ourselves that there is a Turing machine which when we run prints its own description. Well, it was so easy because all the work was done when we were actually proving the recursion theorem. Once we have proved it, we can use it, and all the techniques that we'll have to apply over and over again, we don't need to apply them over and over again. We can just appeal to the recursion theorem. What does the recursion theorem say intuitively? It says that a Turing machine can get its own description and compute with it. The recursion theorem says that a machine can obtain its own description and can go on to compute with it. By using the recursion theorem, we can add the following statement to our informal description of any TM that we are designing. Obtain own description self. So, you can think of the recursion theorem as some sort of a mysterious function call, and when the machine makes this mysterious function call, what is returned from that function is the program itself or the description of the Turing machine itself. Once we add this informal statement to our programming language, we can actually have very powerful programs. Let's consider the following Turing machine M. On input W, obtain own description self and now print self. This machine prints its own description. It is so easy to design using the recursion theorem or when we have the recursion theorem at our disposal. So, using the recursion theorem, it's a triviality to design a machine which prints its own description. The machine actually gets its own description, which it is allowed to do because of the recursion theorem, and simply prints it out. Let's talk about computer viruses. Computer viruses are programs that copy themselves into different parts of a computer system and infect it. How can one write a computer virus? Well, one way to write a computer virus is to actually use the techniques that we are learning in the recursion theorem. A computer virus first obtains its own description, then analyzes the system, the computer on which it is running. It finds out places where it thinks it can safely copy itself, and it starts copying itself. That is one way that we can write a computer virus. This is an application of the recursion theorem. Of course, this is an extremely negative application of the recursion theorem. We will do much more interesting and useful things with the recursion theorem. One thing we can do with the recursion theorem is to obtain a very simple, nice and intuitive proof that the halting problem is undecidable. Remember ATM, the halting problem? Remember that language in which consists of all pairs M, W such that M accepts W. We know that this language is undecidable. We already proved it, and the proof was brilliant. It used a diagonalization technique. Now, we will prove the same thing, that the halting problem is undecidable using the recursion theorem. Let's prove that ATM is undecidable. Suppose ATM is decidable. Then there is a decider H that decides ATM. What we will do now is take this decider H and the recursion theorem to come up with a new Turing machine which we call B. Here's a description of B. On input W, the Turing machine B obtains its own description. It's allowed to do that because we have the recursion theorem. Now, B runs H on B, W. That means its own description followed by W. If H accepts, then it rejects W, and if H rejects, then it accepts W. Clearly on any input W, B does the opposite of what H declares it does. Therefore, H cannot be deciding ATM. Simple. So, this was a few lines of which were needed to prove that the halting problem was undecidable. That's because we have all the power of the recursion theorem with us. Let's look at this proof a bit more closely. Let's see how we are actually applying the recursion theorem. How are we constructing this Turing machine B? Actually, what we do is we first look at this Turing machine T, which is slightly different than B. T is a Turing machine that gets input M, W. And what it does, it runs H on M, W. If H accepts, it rejects. And if H rejects, then it accepts. So this Turing machine T is actually made by using H. So if H exists and is a decider, then this Turing machine T exists. Once we have this Turing machine T, we can apply the recursion theorem. And the recursion theorem says that there is another Turing machine which we call B, and B only takes W as an input. And what does B do? Well, let's mechanically follow the recursion theorem and see what B exactly does. B will be computing a function little b such that B of W is going to be T of B, W. But T of B, W is equal to accept if and only if H rejects B, W. Thus, B accepts W if and only if H rejects B, W. Hence, the language of H is not ATM. So, this is the details of how we use the recursion theorem in order to prove that ATM is undecidable. Of course, if you think about it informally that a machine is allowed to get its own description, then the proof becomes more transparent and it's easier to see that it's a correct proof. Let's go on and do another application of the recursion theorem. Let the length of the description of a Turing machine be the number of symbols in its description. We will say that M is minimal if there is no Turing machine which accepts the same language as M and has a shorter description. So, what we are interested in is minimal Turing machines. In some sense, the smallest, the shortest Turing machines that accept a given language. As you know, to accept a given language, I can have more than one Turing machine which accepts that given language. Well, I'm interested in the shortest Turing machine, the one whose description is the shortest. All those Turing machines which are shortest for the language that they accept will be called minimal. Of course, this is a very interesting set because if I were to be able to find out a minimal Turing machine, then I could do compression. For example, if I want to send you a string which is very long, instead of sending you the whole string, I could send you a short program that outputs that string or that accepts that string. This would be a very nice way of doing compression. Well, so min-TM is the set of all minimal Turing machines, all Turing machines which can't be made smaller. If we try to make them smaller, we cannot accept that language. Let's look at this set and say a few things about it. What we will prove is that min-TM is not Turing recognizable, and we will use the recursion theorem in order to do this. But before doing this, let's collect two simple facts about min-TM. The two facts about min-TM are the following. Firstly is that min-TM is infinite. It contains infinitely many Turing machines. That's obvious since there are infinitely many languages, infinitely many Turing recognizable languages, and for each language there must be exactly one Turing machine in min-TM, so the total number of Turing machines in min-TM is infinite. The second little fact is that min-TM contains Turing machines whose length is arbitrarily large. So, min-TM would contain Turing machines whose length is arbitrarily large because if there was an upper bound on the length of the largest Turing machine in min-TM, then min_tm would be finite. So the second fact is actually a consequence of the first fact. Now, if min_tm is Turing recognizable, then there exists a numerator E that enumerates min_tm. We will use E and the recursion theorem to construct another Turing machine which we will call C. Let's look at the description of this Turing machine C. On input W, this Turing machine obtains its own description. This is where we are applying the recursion theorem. A Turing machine is allowed to obtain its own description because of the recursion theorem. Now what this Turing machine does is it runs the enumerator E, which starts enumerating machines which belong to min_tm. Since min_tm is infinite and it contains arbitrarily large Turing machines or Turing machines whose description is arbitrarily large, therefore eventually a machine D will appear whose description is longer than the description of C itself. Now what C does is once it finds a Turing machine D whose description is longer than itself, it simply starts simulating D on W. So what is C doing? It is waiting for a machine to be enumerated which is longer than it, and then starts simulating that machine on the input W. So C will behave like a machine which is longer than itself. Well, C will behave like a Turing machine D which is longer than C. Well, this means that D is not a minimal Turing machine because C accepts the same language as D and C is shorter than D. Therefore, the enumerator is not enumerating min_tm and hence min_tm is not a Turing recognizable set. Actually, the same proof can be used to obtain an even more interesting theorem. That theorem says that every infinite subset of min_tm is not Turing recognizable. So, in that sense, min_tm is an extremely difficult set computationally. Not only it is not Turing recognizable, but all its infinite subsets are not Turing recognizable. Next, what we want to do is prove a fixed point theorem using the recursion theorem. Let's look at the statement of this fixed point theorem. This theorem says that let T be a computable function from sigma star to sigma star. So some Turing machine can compute this function little t. Then there is a Turing machine F, which is what we say is the fixed point. There's a Turing machine F such that T, when applied to the description of F, accepts the same language as F. We should think of this computable function T as a function that scrambles programs. So it goes and makes some syntactic changes to the program. What this theorem says is very interesting. It says you can try to write a program that takes other programs and scrambles them. And you can try to be as bizarre, as weird, as complicated as you want. No matter how complicated this function T is, there will be one program which it will not be able to scramble, in the sense that the scrambled copy of the program will behave exactly like the original copy. This is a very interesting theorem, and it would be very difficult to prove without the recursion theorem. Now, what we will do is use the recursion theorem to prove this theorem, and this fixed point theorem is not going to be very difficult because we have all the power of the recursion theorem. So let's have a look at the proof. The proof is very easy if we use the recursion theorem. Let us consider this Turing machine F, which is described as follows. Its input is W. First, what it does is it obtains its own description. So using the recursion theorem, this Turing machine obtains its own description, and then it applies T to itself to obtain another description of a Turing machine G. G is the scrambled copy of this Turing machine, and now it simply simulates G on W. So what will be the language accepted by this Turing machine? Well, the language accepted by F would be exactly the same as the language accepted by G, because it's computing G and then simulating G on its input. However, G is the scrambled copy of F. So the language accepted by this Turing machine is exactly the language accepted by a scrambled copy of this program. And thus, the fixed point theorem is proved. It was not hard at all, simply because we had all the power of recursion theorem. The recursion theorem is very interesting and it has many other applications, but this is the last application that we are going to study. Now, we'll move on to another topic. Our next topic is mathematical logic. Mathematical logic is an extremely important and fundamental branch of mathematics, and it studies mathematics itself and how we do mathematics. So in that sense, it's the foundations of mathematics. It really asks foundational questions in mathematics. Let's look at some of the questions that mathematical logic asks and tries to answer. The main questions in mathematical logic are: what is a theorem? What is a proof? What is truth? Can an algorithm decide which statements are true? Are all true statements provable? So as you can see, mathematical logic is not studying numbers or groups or other kind of structures or graphs or Turing machines. Mathematical logic is actually studying the concepts that are very central to mathematics itself. Theorems, proofs. How do we decide whether something is true or not? We are not going to be studying foundations of mathematical logic, but we'll be looking at decidability questions that arise from mathematical logic. Let us look at a few formal mathematical statements and try to understand them, and then we will start developing definitions which will be needed for our study of mathematical logic. So let's look at the following three statements. The first statement says, and let's first read it formally, that for all q, there exists a p, so that for all x, y, p is greater than q, and if x and y are greater than 1, that implies that x times y is not equal to p. This statement looks very mysterious, but let's analyze small parts of it and see what it's saying. So suppose if I tell you that I have a number p such that whenever you take two numbers which are greater than 1 and multiply them, you never get p. Well, in that case, what I'm saying is this number cannot be written as a product of two other numbers. Such numbers are called primes, and you must be very familiar with them. So this statement is saying that p is a prime. So let's go back and read this statement carefully again. What it says is, for every q, there is a p such that p is greater than q and p is a prime. So this statement says that there are infinitely many primes. If you take any number q, you're guaranteed to find a prime after that. This is an old statement. This statement has been known to be true for over 2,300 years, and it was first proved by Euclid. Euclid first gave us the proof that the number of primes is infinite. It is a well-established mathematical statement. Let's look at the second statement. The second statement says that for all a, b, c and n, a, b, c greater than 0 and n greater than 2 implies that a to the n plus b to the n is not equal to c to the n. So, what does this statement say? Well, it says that a to the n plus b to the n equals c to the n will not have a solution if you take n to be greater than 2. It will not have a solution in positive integers. Well, if n is equal to 2, then you do have solutions. For example, 3 squared plus 4 squared is 9 plus 16, which is 25, which is 5 squared. So you have 3 squared plus 4 squared equals 5 squared, and we do have solutions. But if you try to find numbers like a, b, and c, which are all positive, such that a cubed plus b cubed equals c cubed, you will find none of them. If you try to find numbers which are all positive, and a to the 4 plus b to the 4 is equal to c to the 4, you will not find any. And this statement is saying that as long as n is greater than 2, you will never find any solutions to a to the n plus b to the n equals c to the n. This statement is extremely famous, and it was first stated by the great French mathematician Pierre de Fermat. He had actually written that this statement is true, and he had said that he also has a very clever, very beautiful proof of it, but the proof was not provided by him because he said that in that particular paper he did not have space for that proof. Well, Fermat died without revealing the proof, and it took 400 years to find the proof. And many mathematicians believe that Fermat did not have a proof. Some of them believe that he may have had a flawed or an erroneous proof which he thought was correct. This statement is extremely non-trivial to prove. It was recently proved in the 90s by the great mathematician Andrew Wiles. So this is an example of another statement which looks very simple. It's a mathematical statement, it's extremely deep, and finding a proof has been a great challenge for mathematicians, and they have eventually done it. Let's look at the third statement. This statement says for all q, there exists a p such that for all x, y, p is greater than q, and you see there it says that p cannot be written as a product of x and y, and p plus 2 cannot be written as a product of x and y. So what does this statement say? Well, it says that no matter what number q you take, I can find you a prime number p such that p is going to be a prime and p plus 2 is going to be a prime. Such primes are called twin primes. For example, 3 is a prime and 3 plus 2, 5 is a prime. So 3 and 5 are twin primes. 11 and 13 are another example of twin primes. And what this statement says is that no matter how large of a number you take, you will be able to find twin primes beyond that number. In other words, there are infinitely many twin primes. So Euclid's theorem said that there are infinitely many primes. This statement says there are infinitely many twin primes. This seems to be a very simple statement. However, nobody knows whether this statement is true or not. In fact, if you were to prove this statement, you would become very famous overnight. This is an extremely well-known conjecture, extremely important conjecture in number theory, and finding a proof of it would be spectacular. So we've seen these three statements which look very simple. They're formal statements in number theory, and the status of these statements is as follows. The first statement is known to be true for 2300 years. The second statement is true and took about 400 years to prove. The last statement is a famous open problem. What we want to do is, now we want to study these statements very formally. We want to make all these notions very precise. So we start with this alphabet which has or, and, negation, the two parentheses, there exists for all, x, and some things which we are going to call relation symbols, R1 up to Rk. Well, as you know, or, and negation are Boolean operators. We have two parentheses. We have two things which we are going to call quantifiers. One of them is for alls, and the other is they exist. These are two quantifiers we will have. And then we will have things called relation symbols. They will be denoted by R1 all the way up to Rk. Note that if we need more than one variable, we can use x for the first variable, xx for the second variable, xxx for the third variable, and so on. However, we will write them as x1, x2, and so on because it's less cumbersome. We will also allow some other Boolean operators like an implication. Thus, P implies Q is actually a short form for writing Q or not P. So, as you know, and, or, and not are Boolean operators from which you can also get all the other operators. Therefore, we will formally say that these are the only 3 operators allowed, but when we write statements, we'll allow ourselves to write an implication. Right now, what we have just done is defined an alphabet. Let's go further. Now we will define what a formula is. Suppose we have a relation symbol Ri, then Ri, x1, x2 up to xj is called an atomic formula. The value j is called the arity of the relationship symbol Ri. All appearances of a relation symbol must have the same arity. So, if you have a relation symbol which has arity 3, throughout the formula when you write, it must have arity 3. That is one restriction. And when you write a relation symbol and put variables in it, that's an atomic formula. Once we have defined an atomic formula, we're going to define what a general formula is. And a general formula is defined inductively or through the principle of recursive definition as follows. A formula is an atomic formula, and if phi1 and phi2 are 2 formulas, then phi1 and phi2, phi1 or phi2, and not of phi1 are also formulas. Similarly, if phi1 is a formula, then there exists xi, phi1, and for all xi, phi1 are also formulas. So this is how you can make formulas, is by applying these operators and making more and more complicated structures which we will call formulas. A quantifier can appear anywhere in the formula. The scope of a quantifier is the fragment of the formula that appears within the matched parentheses or brackets. We will assume that all formulas are in something called pre-Nix normal form, where all the quantifiers appear in front of the formula. A variable that is not quantified with the scope of a quantifier is called a free variable. Let me say something about the pre-Nix normal form. What we are insisting is that all the quantifiers should appear in the formula, and then you can have a very complicated formula. Well, it is well known in logic, and it's a technical theorem, that every formula can be converted into pre-Nix normal form. If you think about it, that's not too unobvious either. It's intuitively, reasonably very clear. However, we will skip the proof that every formula can be converted into an equivalent formula in pre-Nix normal form and take that theorem as a face value. So all the formulas that we will talk about from now on would always be in pre-Nix normal form. This means all the quantifiers appear before, and then you have the formula. A sentence or a statement is going to be a formula which has no free variables. Let's look at an example to clarify this concept. The first formula is R1 of x1 and R2 of x1, x2, x3. This formula has 3 free variables, x1, x2, and x3. They do not come in the scope of any quantifier, therefore they are 3 free variables. Let's look at the second formula. That's for all x1, R1 of x1 and R2 of x1, x2, x3. In this formula, x1 is not a free variable because it comes within the scope of a quantifier, whereas x2 and x3 are free variables. Let's look at the third formula, which says for all x1, there exists x2, there exists x3, R1 of x1 and R2 of x1, x2, x3. In this formula, all the variables are not free, they are bounded, they come within the scope of the quantifiers. Therefore, this formula has no free variables, and we will say that this formula is a sentence. So far, all we have done is defined syntax. What is a syntactically correct formula? These formulas have no meaning, they have no semantics. So what we want to do is define the semantics of this formula. In order to do that, we will need 2 other ingredients. One is going to be the universe. That is going to be the universe where the variables can take values. The other is going to be the interpretation of the relation symbols. Once we have put these two things together, we will actually define the semantics of these formulas. Let's have a look at how do we do that. Let us now specify the two items that are needed to give meaning to these formulas. One is the universe over which the variables will take values. The other is assignment of specific relations to relation symbols. Recall that a relation is an assignment of k tuples in the universe to the set true, false. So what we do is we specify a universe and we specify what is the meaning of each relation symbol. The relation symbol itself has no meaning, but once we say that this relation symbol stands for a particular relation over the universe, we give it meaning. Specifying of the universe and the relation symbols is what is called a model. Let's look at what a model is formally. A universe with assignment of relations to the relation symbol is called a model. Formally, a model M is going to be a tuple U, P1 up to Pk, where U is the universe and P1 up to Pk are relations assigned to R1 up to Rk. We refer to the language of the model to be the collection of all formulas in which each Ri has the same arity as Pi. Now suppose that R1 is the only single relation that we have and it happens to be assigned P1 which has arity 5. Then we will be looking at all formulas in which R1 actually appears with arity 5. Well, once we have assigned a universe and the relations to the relation symbols, what we have is a model, and a sentence can either be true in this model or it can be false in this model. If the sentence is true in the model M, then we say M models that sentence. If we have a sentence phi which is true in a model M, then we say M is a model for phi. We have defined quite a few things. It must be quite overwhelming. So let's look at a specific example and see what we are trying to do. So what we are going to do now is look at a few models and sentences and see what we are trying to do. Let's consider the sentence for all x, for all y, R1 of xy or R1 of yx. As you see, this formula is nothing but syntax. It's just a syntactically correctly written formula and it has no meaning. Once I tell you what is the universe for x and y, this formula will start making more sense. The universe could be anything. For example, I could say the universe is the set of all cats in this world. And R1 means that a cat is related to another cat. So R1 of xy means x is the mother of y. And then this will become a sentence about cats. But suppose if I make the universe something else as numbers, then this sentence will have a meaning. It would be talking about numbers. So let's look at two particular examples of models for this sentence. Let us take the first model M1, where the universe consists of all natural numbers. So right now we are saying that the variables can take values over natural numbers. And the only relation in this model is the usual less than or equal to relation. So R1 corresponds to the relation less than or equal to. So R1 of A comma B is the same as A is less than or equal to B. If we do that and look at this sentence in this model where the universe is the natural numbers and the relation is the less than or equal to relation, then what does this sentence say? It says for all x and for all y, x is less than or equal to y or y is less than or equal to x. And as you know, this is then a true sentence. If you take two integers, x and y, either x is less than or equal to y or y is less than or equal to x. So this sentence is true in this model, or M1 models this sentence. Well, we can look at another model and see whether this sentence is true in that model. So let's look at the other model, M2, which is the same as the universe is once again the same. It's the natural numbers. But now what we do is we assign R1 the relation strictly less than. So this model assigns R1 the relation strictly less than. So R1 xy means x is strictly less than y. Well, then what does this sentence say? Then this sentence say for all x and for all y, x is strictly less than y, or y is strictly less than x. Is that sentence true? And once again, remember that your universe is the natural numbers. Well, this sentence is not true. For example, if I take x to be equal to y, then x is not strictly less than y, and y is not strictly less than x. And this sentence is not true. So this sentence is true in one model, and it is not true in another model. That should not be surprising. Sentences are true when you make the context clear. So when you make the universe and the relations clear, then they become true or false. For example, you can easily make a statement which is true for all humans, but it's not true for all animals. So, in order for your sentences to be true, you must specify the precise universe and also what the relation symbols mean. You must assign them to specific relations. And that gives you a model, and that can make a sentence true or false. Let's go further. Let's do another example. Here we have a sentence which says for all y there exists x, R1 of x, x, y. That is our sentence. It has only one relation symbol. This sentence is going to be true or false depending on what model we are talking about. So what we want to do is look at in what models this sentence is true and what models this sentence is false. So let's do the following thing and say that R1 is going to be assigned the relation plus. More precisely, let us assign plus to R1. Plus of a comma b comma c is going to be true if a plus b is equal to c. Then is this sentence true? What is this sentence saying? For all y, there exists an x such that x plus x equals y. So, in other words, is it true that for every number y, you can find a number such that x plus x is equal to y? Is it true for every y? Well, as you can see, I have not still specified the universe, although I have given you the meaning of R1, which I am going to interpret now as plus. I have not told you what the universe is. Suppose now, if I tell you that the universe is the set of all integers, then is this sentence true? Is it true that for every y, you can write it as x plus x? Well, it's not true. For example, 3 is not the double of any integer, whereas 4 is. So for integers, this statement is not true. On the other hand, if I were to tell you that this statement is about real numbers, then is it true that for every y, there exists an x such that x plus x equals y? Of course, in that case, you can take x to be y over 2. And then y over 2 plus y over 2 would always give you y. So this statement is true in real numbers. So once again, if we take the first model, which is the set of all natural numbers, along with the plus as the relation that is assigned to R1, this statement is false. That model makes this statement false. Whereas if we take the real numbers, along with the relation plus, that makes this statement true. So the truth and the falsehood of a statement depends entirely upon the model. We should not be surprised at this. What we're trying to say is, in order for us to be very sure if a statement is true or not, we must have the clear interpretation of the objects that we are talking about, namely the universe, and we must also have a very clear interpretation what these symbols are referring to, namely the relations. Once we have specified all that, we get a model, and then we can look at a sentence and say whether it is true or not. Suppose we have a model M. Then we define the theory of M. It is by definition the set of all sentences that are true in the language of M. So a theory of a model is the set of all true statements. So what I may be interested in is theories of integers. So I take the model, for example, I take the model natural numbers along with plus and multiplication as my two relations, less than or equal to as another relation, equality as another relation, and then I can be talking about, well, what are the set of all sentences that are true in number theory. Of course, for this to be absolutely precise, I must clearly define what addition, multiplication, what less than or equal to is. Otherwise, there would be confusion. So, a theory of natural numbers is the set of all sentences that are made true by that model. What we are interested in is, if we have a model, which sentences are made true by that model and which sentences are made false by that model. The set of all sentences that are made true by that model is called the theory of that model. A central question is going to be whether, by looking at a sentence, if we can decide whether the sentence is true or not. So, in terms of decidability theory, what we would be interested in finding out is if theory of a model is a decidable set, whether it is Turing recognizable or whether it is undecidable. That is a central question that links logic and decidability theory. This lecture has been a lot of definition, very basic definitions in logic, and you must revise these definitions. In the next lecture, we will use these definitions and actually look at decidability questions about logical theory. I'll see you next time. Thank you and goodbye.